Let's get started. In today's lecture, I would like to talk about laser diodes. So, if you look at the history of semiconductors in the last 70 years, there have been two great inventions, or rather, in terms of broadly technology, there have been two great inventions. One of them is a MOSFET. It has changed the electronics industry, and it has made computing possible. The other invention was a laser. This is also a nonlinear device, similar to a transistor, and essentially instead of generating electrons or controlling the flow of electrons, you're actually generating light. You can turn it off, turn it on, right? So in a laser, we build upon the concepts of LEDs to discuss lasers. But what laser has done is, it has enabled communication revolution. So in the olden days, there were copper wires connecting cities, and it used to take it was a lot of effort to actually make a phone call. They used to call it trunk call, and it used to take a long time to actually make a connection. You have to fix a time and all that. But now you have, internet. Within seconds, you can communicate anywhere in the world, and you are able to download, and you're able to have so much of information at your fingertips. The reason this has been possible is information transfer revolution that has happened in the background. You don't see it in your homes, but everywhere you have fiber optic connections nowadays. Almost the homes you have fiber optic connections nowadays, right? So what's happening is you're transmitting information over a fiber, and that information is transmitted at a wavelength of 1.55 microns, and the backbone of that is a semiconductor laser. So without the corresponding increase in the technological development of lasers, it is not really exaggeration to say that the current information technology revolution would not have been possible. Okay, you might have a supercomputer, but if you cannot access it or if you cannot connect it to internet, there's no use of a supercomputer, right? Only a few people would have access. So in essence, yeah, lasers have changed the world, and we would like to understand some aspects of it, especially only the semiconductor lasers. We will not focus on the general lasers. We'll only focus on the semiconductor lasers. All right. So I have already introduced the concept of stimulated emission in the beginning of the discussion this week. So what we said was you have these three different processes: absorption, emission, spontaneous emission, and stimulated emission. So I don't want to repeat it. Only just want to say that in stimulated emission, you're able to, if you have a single photon incident, you can have two photons generated with the same phase and frequency. Okay, it's coherent process is what we said. So this is a two-level system, and if you look at the population densities in a two-level system, it turns out that you can write the ratio n2 by n1, and it follows the famous Boltzmann kind of statistics, wherein the probability of occupation of the higher level is proportional to the energy difference between the levels. Okay, so what this essentially tells you is that if you have thermal equilibrium, just consider equilibrium, then the population density of the higher state is always lesser than the lower state. Okay, so N2 is the population of the higher state, and thus will be lesser than N1. Okay, and this is typical for all the systems, normal systems. Okay, so we have already looked at absorption, right? Absorption is proportional to the density of atoms in the lower state. If you have a lot of atoms in the lower state and there is vacant state, of course, in the higher state, then you can have absorption. So absorption is proportional to N1, right, lower state. Whereas I can say emission, especially stimulated emission, not normal emission. Okay, stimulated emission is proportional to N2, right? We want to have states that are available. We wrote out the rate equations in the first lecture of this week, right? So stimulated emission is proportional to N2. That means if you have higher number of electrons in the, larger number of electrons in the higher state, then you can have stimulated emission possible. So from this, it seems that, absorption is always stronger than emission, right? The conclusion seems to be that because we have equilibrium, N2 is always smaller than N1. So we can say that absorption is stronger than emission, right? This seems to be the most typical case. Well, it turns out that we can actually change this condition by what we call as pumping. Okay, we can pump a material with light, right? Let's say if my energy difference, I'll call this as h nu equal to, let's say, E2 minus E1, just any two levels. It could be conduction band and valence band, or it could be states in an atom and so on, whatever. Right? The energy difference, let's say, is E2 minus E1. I can pump, I can supply. I don't know why my I can supply photons with energy, photons with energy greater than h nu. If I do that, higher energy photons, if you supply, you will actually pump it, and then you can create electron hole pairs, and they'll relax to the band edge and so on. So this is called as optical pumping, right? Like we saw in the case of LEDs, where you supply a blue photon to excite a phosphor. So you're supplying a higher energy photon. That's an optical pumping process. You can also have electrical pumping, by which we mean that, like in a laser LED, right? We have seen you can supply minority carriers. You can inject minority carriers and create a situation where you can have a higher population of electrons in the higher state. So we can create a situation where you can say N2 is greater than N1. Okay, and I call this is very, very important, and I call this as population inversion. The regular way population is distributed is N2 is less than N1. That's a Maxwell-Boltzmann distribution we mentioned here. Maxwell-Boltzmann distribution. This is the regular trend. But if I create pumping, optically or electrically, I can create population inversion, which leads to what we call a stimulated emission. Okay, this is necessary condition for stimulated emission. All right. So there are essentially three conditions necessary. One is you need to have stimulated emission process. You need to have gain, and you need to have what is called as cavity. We will discuss that in this video. Okay. So we'll just qualitatively talk about them. So this is population inversion. So what happens if you have population inversion? Well, you can achieve amplification. How do we achieve amplification? Well, you caused N2 greater than N1, right? Then let's say a photon is incident. We saw that it emits a second photon, right? So let's say you created a situation where N2 is greater than N1. So one photon is causing another photon, right? So you have two photons. Now those two photons, if they pass through the material with N2 greater than N1, then they cause four photons to be generated. Two more photons will be generated. And those four photons will cause 8 photons to be generated. So we are essentially amplifying the number of photons, increasing the number of photons. And so this can be captured by, we can write a rate equation for this. We can say that di nu, I'll say, the intensity of photons at a particular wavelength by dx is going to be equal to, of course, you have this gain, you have this, condition satisfied, population inversion. When you have that condition satisfied, the number of the increase, the rate of increase in the intensity is going to be proportional to the existing intensity. So there's going to be I nu, and then there is a coefficient that captures the amplification. We call it gain, and we say that is gamma equal to this. Okay, so basically we have this, which we are calling as gain in the material, gain in semiconductor. All right. So how is this gain possible, right? So this gain essentially is going to be proportional to gamma of nu is going to be proportional to N2 minus N1. Is it wavelength dependent? Well, of course it is wavelength dependent. The reason is we have seen that the spectrum, right? Emission spectrum of a semiconductor. We said it's going to be of this shape, right? So essentially what it means is that you have electrons in the higher energy level at this energy, where these differences in energy, right? So if you talk in terms of, yeah, the range over which N2 is greater than N1 is going to be Eg on the lower side, and on the higher side, it is going to be the difference in the Fermi energy, EF, let's say N minus EFP. Okay, so that is the range over which you can have N2 minus N1 satisfied. Okay, so because of that, wherever the extent of N2 minus N1 is going to determine the gain. And whenever you have photon emitted, it is going to reduce this population inversion. For example, if you take, let's say, let's take a state, higher state N2, let E1, E2. Okay, there are two states, and this has a population of N2 equal to 10, and this guy has a population of 0. Just as an example. Okay, now if a photon is incident, what happens? Well, it will cause another photon to be generated, right? So when a photon is generated, what happens to the N2? Well, one electron is going to come down to the lower state. Only when it comes down to the lower state, it emits a photon, right? So N2 population reduces to 9, whereas N1's population goes to 1, right? One electron has come into the lower state. So this has happened. So now you have two photons. And when these two photons go to the, it's still the same material, right? So it can cause another two photons to be generated. So if you have another two photons to be generated, the population of higher state reduces to 7, and this guy increases to 3. Now you have 4 photons, and these 4 photons can cause 4 more photons to be generated. So quickly this becomes 3, and this guy becomes 7. So if you monitor N2 minus N1 in this scenario, N2 minus N1, N2 minus N1, this was initially 10 here, then it became 8, then it became 4, then it became actually negative. So it became less than 0. So very quickly, the population inversion is destroyed, right? And we said that if you want to have amplification, we need to have N2 minus N1 greater than 0, right? N2 has to be always greater than N1, right? So as long as you maintain this condition, right? N2 minus N1 greater than 0, amplification occurs. Amplification continues till gamma of V or nu is greater than 0. The moment it becomes less than 0, it just will not amplify anymore. It will simply absorb photons. Because now lower state has, let's say, 7 and upper state has 3. The photon can easily excite an electron to go from lower state to higher state. So it can get absorbed. Okay, these are competing processes. Okay, so whenever you want a laser, we have to ensure that the N2 minus N1 is greater than 0. The way we do that is, as I said, pumping. So it's not enough if you just simply supply a photon. You just have to continuously supply these photons. All right. One moment, just let me pause this. I'll get back. Excuse this. All right. Sorry, there was a small audio issue, so I had to check that. All right. So yeah, the necessary condition is that you have to keep pumping. Okay, pumping is necessary to create amplification. And if you want to create lasing, that is, very, very strong amplification, we need to satisfy one more condition, which is basically to select a certain wavelength, because gain can happen over a range of wavelengths. As you saw in this picture here, you have gain happening over a range of, wherever the spontaneous emission happens, those range of frequencies can actually get, support, amplification. But it is not enough. We need to make sure that there is a cavity that selects the photons, which particular wavelength should be amplified. And this is known as basically a lasing cavity. For example, we mentioned, you might have definitely encountered a system between two, rigid supports, or even a quantum well, right? Whatever you want to call it. So you can have, let's say, two supports, or a potential well maybe. What are the wavelengths that are supported by this? Well, the wavelengths are supported will be L equal to N pi. Whatever wavelengths for which you have integral multiple of wavelength is equal to L, those will be supported by this structure, right? Similarly, what we can do is we can make a heterostructure that we have discussed in the last couple of lectures, and you cut the faces, facets. Take a piece, cut edges of it, okay? Make them atomically smooth, okay? So that can be easily done. It's not that difficult to do. So when you do that, you have a piece of semiconductor. This case, you are actually seeing the three-dimensional picture. So this is your, contact, one contact. So actually you have the heterostructure in this direction. So you have the confinement regions, basically here. These are the confinement regions. And the blue one is the active region, where you have photons getting emitted. So, and then physically you chop it and then you make it a certain size. Maybe this length can be length of 100 microns maybe. Okay. When you do that, you're essentially creating, this is a high index. Remember, all the semiconductors have nearly same index, 3.5, let's say. Outside is air. So when the photon comes near the interface between, the outside here it's air, right? This is air, let's say gallium arsenide interface. Similarly, on the other side, you have air gallium arsenide interface, and we know that it primarily reflects. When it reflects, you have this sort of a cavity formed. Essentially, the reflection photons have to basically be confined between these two mirrors in some sense. This ends will act like a mirror, okay? And we call this as Fabry-Perot cavity. Just if you want to know more, you can look up. Essentially, the idea is that the photons are confined to region of space of certain length, okay, in the lateral direction, okay, and these give rise to what are known as different modes, okay. And qualitatively it is or intuitively it makes sense. Wherever the wavelength is integral multiple of the length is integral multiple of a wavelength, then those modes are supported, and you can have various modes which are supported, discrete modes, okay. We can compute what is the distance between the modes and so on. Now, you also have a gain region over a certain range of wavelengths. Whenever, if the wavelength falls under the gain region here, it will get amplified. So those photons will be amplified strongly. Whereas photons of this mode will not be amplified strongly. They are weak. So they will decay. And here also they will decay. Only those photons which fall into the center region will get amplified. And so the intensity increases. And then they'll hit the one end. For example, you have a cavity. Your photons are going, they get amplified, they'll hit this part and then turn back. They come back. Again, they get amplified further, again come back. So there is a circulation of energy in that. So this causes the energy to be building up in the cavity, okay, which causes lasing. Laser is very similar to a resonator. Now you might have, resonator or oscillator. You might have studied oscillating circuits, right? Wherein you are supplying energy from outside, from using a power supply, and then you are causing a buildup of oscillation. When you satisfy certain feedback conditions, you are actually having a buildup of oscillation, and then you have large amplitude that is generated, right? Exact same thing happens in a laser. So this cavity is essentially providing the feedback. You have the gain that is provided by the semiconducting material, and the cavity is providing the feedback, which is causing one single wavelength to be selected. Okay, this is the principle of laser, essentially. So for lasing to occur, you need to satisfy three conditions. One is you need to have stimulated emission, you need to have gain, you need to have a cavity. Okay, so how do you get gain? By pumping. How do you get a cavity? By mechanically, adjusting the size of your cavity. Okay, so if you make the size of the cavity smaller, your distance between the modes increases. So it turns out that you can have lasing at a single mode or multi-mode and so on, okay, depending on how much is your gain bandwidth. Now we call this width as a gain bandwidth. Now this particular guy has gain bandwidth. Depending on how much overlap is there between the gain bandwidth and the mode in the cavity, you can have amplification, a laser. Okay, so if you look at the IV characteristics of a laser, right, they look, or rather, you should not call it IV characteristic, we should call it LI characteristic. So you're having the input is a light and the output is, input is current and output is light. So we call them LI characteristic, light versus current, correct? Li characteristics. They look very similar to Li characteristics. They look very similar to the typical IV characteristics. So there is a threshold. So only when your gain increases beyond a certain threshold, then you have amplification. So you see that sort of a threshold-like behavior that is shown. Okay, and this threshold is very sensitive to temperature and so on. I just wanted to show you how similar it is. That's it. Okay. So whenever you have laser, you can talk about, you can plot it in a logarithmic scale and look at how it looks like and all that. So there is a lot of similar analysis that you can do. So once you understand semiconductors very well, you could also understand these lasers very well. All right. So I don't want to I don't want to get into all these details. Just wanted to show you how it looks like, and I just also wanted to mention how LED is different from a laser. So we saw that in LED, right, you have emission over a range of wavelengths. For example, we said theoretically that was 1.8 kT. Practically, it will be about, let's say, 30 nanometers, 30 to 50 nanometers maybe, right? Practically, that will be the typical range of an LED. But laser, it turns out that because of the feedback, you have a very good oscillation at a single wavelength, almost, you know. So there are a lot of differences between lasers and LEDs. For example, you take an oscillator, right? Electronic oscillator, maybe if you have studied analog circuits. Initially, you'll start out from noise. Various frequencies are present, but over time, only one particular frequency will be selected. The same thing happens in lasers. You have a particular wavelength that is generated. So what are the differences between LEDs and lasers? So we can list a few of them just for your knowledge. The first one already I have mentioned is that LED has delta lambda of, let's say, 30 nanometers. Whereas here, delta lambda will be less than 1 nanometer, ideally. Okay, so it's very, very monochromatic. And that is why this is useful. The emission profile, if you look at it, the LED emission profile is what is called as Lambertian. Basically, it means, we don't need to get into it. It's proportional to cosine square theta. So LED emission will not be in a straight line, but it has a certain angle spread over which it emits. It's not a directional emission. Okay. Whereas in a laser, it is directional emission. Okay. Number 3, because again, the same, the delta lambda is small, and in this case of LED, we have delta lambda large. So we can say that LED is incoherent. Okay. Whereas laser is a coherent source. For example, if you take communications, right, you might have studied that you want to supply one single frequency. You would like to deal with ideal frequencies, sinusoids, right? Monochromatic sources. LED is a monochromatic source. Sorry, not LED. Laser is a monochromatic source, whereas LED is not coherent. Okay, and in LED you have spontaneous emission, whereas in a laser you have stimulated emission. That is again the difference, right? And LED does not have anything like a threshold. It can simply keep emitting, right? Well, I mean, yeah, if you supply above a certain current, you'll start seeing generation of light. If it's a direct band gap semiconductor, you will have light right from the beginning. So there is nothing, intensity can be increased, threshold less, I would say. Here you should have a threshold. Okay. And lastly, applications. LEDs are used for lighting mainly, or everywhere, right? A lot of lighting, even lighting. Lasers are useful for communications. Okay. So by the way, this reference is wrong. It's a leftover thing. Okay. All right. These are the main differences between LEDs and lasers. Okay. So how does a laser output look like? I'm sure all of you have seen a laser pointer. You'll have a single beam which is nicely traveling. You can actually, if you pour some dust or something, chalk, you just hold a chalk and then you dust it. You'll see that line nicely, beam of lights that are propagating because of lasers. And you can tune these lasers from 400 nanometers. This will be nearly 400 nanometers. This will be nearly 700 nanometers. So you can tune the wavelength of operation of a laser. and they're very, very useful for research purposes. This is visible laser. You could also have IR lasers. In this case, I'm just showing you how a laser is tunable from 1520 to 1620 nanometers. This is centered around all important lambda equal to 1.55 microns, which is the telecommunications wavelength. Okay, so by tuning this, we are telecommunications. We call it C band, communications band. In that, if you're able to tune a laser, we can multiplex many channels. So optical fiber is single fiber, right? You can send many different wavelengths, and we call it WDM, wavelength division multiplexing. You can have WDM because of which you can have multiple channels, very closely spaced channels, and you can communicate a large amount of information. That's why the bandwidth of optical fiber is huge compared to electrical wire. If you take a simple electrical wire, we cannot really send very high bandwidth because at some point RC delays will come into picture, and you can't multiplex different signals on the same wire. You can't put two sources and drive it, right? Then there'll be interference because electrons by nature, they interfere. Whereas photons do not interfere. So you can put multiple channels on the same waveguide and you can transmit and get huge bandwidth enhancements. So one of the research frontiers is basically now to integrate this, optical waveguides onto a chip, because we have seen that the processing speeds have saturated because of RC delays. So one of the research domains that is very important nowadays is nanophotonics, wherein you try to integrate photonic ideas, or these lasers onto a chip. Okay, there are many challenges, but also it's a very exciting frontier. So yeah, there's a lot of research work that is going on, and yeah, this is completely open dimension right now. All right. So yeah, that concludes nearly my discussion on lasers. It's very close to my heart because I happen to be working on lasers and nanophotonics for my research. And if you find some of this interesting, you can always write an email to me and we can talk about some internship opportunities and things like that, provided you have done well in the course, of course. All right. So yeah, it's been my pleasure offering this course. And I hope that you have understood, at least you got a bird's eye view of various aspects of semiconductors and their applications. And if you are interested, you could always pursue various subsequent courses that will take you in greater depth. All right. With that, I'll conclude my course. I had a great time. I hope you enjoyed it too. Right. I'll see you some other course. Thank you so much. Take care. Bye.